Hi everyone, my topic is Insights into Paleo-hydrology of the Coorong Lagoon, South Australia, based on radiogenic and stable Strontium Isotope Tracers in fossil carbonates. So this elongated lagoon located along the southeast coastline is the Coorong. And together with the lower lakes, they form an estuary system that terminates Australia's largest river system, the River Murray. So the lagoon itself is divided into North and South Lagoons through this narrow channel at the Punka Point. And the lagoon receives seawater through the Murray mouth and also river and lake waters through the barrages. Also at the southern end, the lagoon receives fresh to brackish continental waters through the Salt Creek. Also, there are localized groundwater inputs into the Coorong throughout the whole region. So as a result, the Coorong Lagoon has a large salinity gradient ranging from marine, which is like seawater in the North Lagoon, and the hypersaline in the South Lagoon. So at the moment, the government is trying to improve the water condition and save the degrading ecology related to such hypersalinity in the South Lagoon. But before making any decisions of putting water sources into it, it is essential to gain knowledge on the past water conditions of the South Lagoon. So my study uses radiogenic and stable strontium isotopes to constrain water sources and carbonate dynamics in coastal systems. Specifically, the radiogenic strontium isotopes, this 87-86 strontium ratio is only sensitive to radiogenic processes. Therefore, is a good tracer for water sources. So in coastal systems, this signature in water, in biogenic carbonate and inorganic carbonate should be identical. On the other hand, the stable strontium isotopes, noted as this 88-86 strontium ratio, is sensitive to carbonate formation and dissolution processes because strontium can substitute calcium in calcium carbonates. And in modern systems, modern environments, such kinetic fractionation between water and inorganic carbonates can be measured. However, to reconstruct the paleo water conditions through fossil carbonates, we need to calibrate this fractionation of stable strontium between modern carbonates and the modern water first. And according to many pioneer studies, such fractionation between in stable strontium isotopes between modern shells and water should be constant regardless of environmental factors. And this forms a basics of reconstructing the paleo water conditions. Here's a cross plot of radiogenic and stable strontium isotopes from a recently published paper with water samples from the modern Coorong region. So these dashed lines depicts theoretical water mixing of different water sources, such as the seawater, the fresh groundwaters, and the lake and the river waters. From modeling of radiogenic strontium isotopes and ratios of conservative elements. These batch of lagoon waters are likely mixtures of fresh groundwaters, the Salt Creek, and the seawater. So for the South Lagoon, you can see that it has about 0.1 per mil horizontal shift of stable strontium isotopes away from the ideal mixing line, which is the amount of isotope fractionation that caused by carbonate precipitation. So this is how we look at the data in modern situation. To reconstruct the paleo-hydrology of the Coorong, first we observe strontium isotopes in paired shell and water samples from these 4 locations of the modern Coorong. And the shell species here is the arthritic hamzai, which will be the same we analyze in the sedimentary cores. In terms of 87, 86 radiogenic strontium, we can see that the paired modern water and shells have some kind of discrepancy. It's likely because that the shells shows an average water signature throughout their lifespan, and while the water changes seasonally. But the stable strontium isotopes between the modern water and shells shows almost a constant offset of 0.1 per mil. And we apply this constant offset to recalculate the paleo water signature. We have 2 sedimentary cores in the South Lagoon, the C18 core near the Punka Point and the core 1 near the Salt Creek. So the C18 core was sampled in 2005, spanning about 130 centimeters and 1700 years based on the Bacon age model. The core 1 near the Salt Creek was sampled in 2019 and is 80 centimeters long. Unfortunately, it only has 1 radiocarbon dating age. At the bottom indicates about 3200 years BP. Here are the radiogenic and stable strontium isotopes of paleo waters calculated from fossil shells throughout these 2 cores. As you can see, based on radiogenic strontium isotopes, the South Lagoon composition has never been dominated by the seawater. And the continental input has always been very important, especially in core 1 near the Salt Creek, and the more recent 1,000-year in core C18. The stable strontium isotopes in core C18 has also been gradually increasing, possibly indicates increasing carbonate formation. While in core 1, this signature seems more stable, although also oscillating. So I plotted these paleo water strontium isotope compositions from the 2 cores back to the cross plot previously. And added all the modern South Lagoon waters I have. What I found is that the modern South Lagoon is even a bit higher in radiogenic strontium than the 2 cores, meaning that the South Lagoon has even become more dominant by continental waters, and seawater is even less accessible. In terms of stable strontium, it's also about 0.05 to 0.1 per mil higher than the paleo Coorong, which means this is an amount of extra strontium isotope fractionation caused by carbonate precipitation. To quantify such strontium removals in the South Lagoon, I used the Rayleigh models of stable strontium isotopes in closed and open systems. So I used the paleo South Lagoon water's signature as the starting point, as well as its plus and minus 1 SD. And these trends depicts the evolution of stable strontiums in the water as the carbonate is being removed. The ending point here would be the modern South Lagoon water signature with its mean value, the plus and minus 2 SD as well. And the projected number is the extra fraction of strontium removed as aragonite, which is where the latter is the main phase of calcium carbonate in the Coorong. And as you can see, the most probable fraction being removed is about 0.2, so 20%. Thanks everyone for listening, and if you have any questions, please go to my session, which is 2.3 in Tuesday afternoon.